So today I'm going to be talking about diffusion tensor imaging and some more advanced diffusion MR methods and its application to children. Specifically, I'm going to cover the topics including defining diffusion, describing why we care about diffusion and diffusion MR. I'm going to review the basic patterns of anisotropic and isotropic diffusion in tissue. I'm going to discuss how MR is made sensitive to the motion of water in a diffusion MR experiment. I'm going to discuss the basics of post-processing diffusion tensor images, including the tensor scalars, fiber tracking. I'm also going to cover some applications to children of these advanced DTI techniques. I'm also going to discuss more advanced diffusion techniques, including high angular resolution diffusion imaging that goes beyond the diffusion tensor model in terms of describing the 3D pattern of water in complex white matter. So what is diffusion? Diffusion is different from flow. If you were brave enough to look out your window this morning, you saw water flowing all over the place. That's not diffusion. Diffusion is the random movement of water molecules, and it's described by this equation, which calculates the mean displacement of water molecules of a certain diffusion coefficient and time. And time is a very important part of diffusion because to observe diffusion, you need to wait a certain amount of time. In this example, I show a collection of red dots that are initially concentrated in the center of this square, and over time they diffuse and occupy the entire box such that the concentration gradient across the box is equal. And if I were to show you any one of these time points, you would not be able to tell me much about the diffusion coefficient. That's because you need to look at two different time points to infer something about the diffusion coefficient. So in the brain, diffusion is blocked by barriers such as axonal membranes, myelin, neurofilaments, basically anything other than water. And I have them here in decreasing importance based on the font size. Axonal membranes is the most important and influential barrier to the motion of water in the brain. Myelin is number 2. And we're very lucky that the brain is so highly organized. In the human brain, there's a concentration of functions on the cortex. That is, all of your voluntary motor function is concentrated in the motor strip. Language, there's a certain language cortices. There's a visual cortex. And following from this concentration and arrangement of function on the cortex is the white matter. The white matter is also arranged in axonal bundles with similar origins, destinations, and functions. And this high degree of organization of white matter bundles is important for diffusion MR because if axons were randomly arranged in the brain, many of the more advanced diffusion MR techniques, including fiber tracking, would not be possible. So let's take a closer look at 3 different modes of diffusion in the brain. You can have isotropic, unrestricted diffusion. This would be the case of free water in the presence of no barriers. Isotropic refers to the condition where the diffusion coefficient is the same in every direction. That is, the mean free path of water in every direction is equal. You can also have isotropic restricted diffusion. And this is also isotropic in that the diffusion coefficient observed in every direction is equal. That is, the mean distance that water molecules displace in every direction is equal, but that distance is less than the free water case. This is because of the random barriers. Anisotropic restricted diffusion refers to the condition where there is a coherent axonal bundle or some sort of repeating elongated structure, such as found in a bundle of axons. And anisotropic refers to the condition where there's a preferred direction of diffusion, that is, diffusion along or parallel to the axons is less restricted, and the diffusion coefficient in this direction is higher than the apparent diffusion coefficient perpendicular to the axons. And this is the fundamental principle behind diffusion tensor imaging. The goal of diffusion tensor imaging is to figure out which direction has least restricted diffusion and tell you the magnitude of diffusion and the orientation of diffusion. So I don't need to emphasize to this group the relevance of diffusion in conditions such as stroke, so I'll quickly go over this. This is how we make a spin echo pulse sequence sensitive to the movement of water. This is your basic diffusion MR pulse sequence, and we've added a dephasing and a rephasing diffusion gradient. These gradients determine the direction that we're probing diffusion, that is the direction that we are sensitive to the motion of water. And if you remember back to one of my first slides, how I said you need to measure diffusion, you need 2 time points. These are the 2 time points. This is the start of our diffusion experiment, and this is the stop, the end of our diffusion experiment. And between these 2 diffusion gradients, we can think of this as the diffusion time. So we're starting by setting up a concentration gradient of phase states, and at the stop, we're observing how far that concentration of phase states displaced. More specifically, in this example, I show 3 individual water molecules, and in this row, the water molecules are stationary during the diffusion time. So during the dephasing, each water molecule is dephased a different amount. During the rephasing, they're all rephased that same amount, such that they're all coherent, producing a high signal. In this case, the 3 individual water molecules are diffusing or moving. So during the diffusion time, they switch positions, and when the rephasing gradient comes on, they're not rephased in a coherent manner, so they're pointing in different orientations, and when you add these together and measure the signal, you get a lower signal. So this is the contrast mechanism in diffusion MR imaging. So this is another graphic illustrating this. If the pattern of diffusion is isotropic with a small diffusion coefficient, that is, water molecules are not moving a large distance, this signal will be bright, as defined by this equation. This equation is your diffusion-weighted signal, your signal without diffusion-weighted gradients, and your diffusion coefficient for the water molecules. If diffusion is occurring at a higher magnitude, that is, the diffusion coefficient is greater, your signal will be dark. You'll have low signal. And in this case, I have anisotropic diffusion, such that if we probe diffusion in the x direction, the diffusion coefficient in that orientation is high. So we get a dark signal. If we probe diffusion transverse or perpendicular to these axons, the apparent diffusion coefficient is low, so we get a bright signal. This is yet another illustration of the relationship between the diffusion-weighted image, the image, this is your echoplanar image without diffusion weighting. The B term, the B value, is related to the strength and the duration of the diffusion gradients, and it's your diffusion weighting term, the diffusion coefficient, which can be calculated for if we acquire the diffusion weighted image and the baseline image. This diffusion coefficient, or apparent diffusion coefficient for a particular direction, is related to the pattern of diffusion. So back to this term I threw out there, B-value. The B-value is related to your gradient strength and the timing of the gradients. And this is a plot of different diffusion-weighted images as a function of increased B-value. And as you increase your B-value, you're decreasing your overall signal intensity, you're decreasing your signal-to-noise ratio, but you are increasing your diffusion weighting, that is your sensitivity to the movement of water, and you're increasing your contrast mechanism, and you're increasing your ability to discriminate and observe anisotropic diffusion. So the next question is, how do we infer the 3D pattern of diffusion? And the answer is to probe diffusion in different directions. If we're imaging celery, this is very simple. If we plot the diffusion weighted signal intensity as a function of B, when we're probing diffusion perpendicular to the celery fibers, the signal remains high. So we can infer that diffusion is restricted and that there's not a whole lot of diffusion perpendicular to the celery fibers. If we're looking at diffusion parallel to the celery fibers, we see that the signal is attenuated much greater in this direction. So we can infer that diffusion is least restricted along this orientation. And from this information, I can tell you how the celery is oriented. But unfortunately, the brain isn't as simple as celery, and we need a more comprehensive mathematical model for describing the orientation and magnitude of diffusivity. And that's where diffusion tensor imaging comes in. So this schematic highlights the overall strategy of a diffusion tensor imaging experiment. So we start with anatomy over here. We have a bundle of axons, and within these axons we have a particular pattern of water diffusion. And this is present whether or not we're performing the diffusion MR experiment. When we perform our diffusion MR experiment, our goal is to figure out what this pattern of water diffusion looks like, because if I tell you what this pattern of water diffusion looks like, we can infer something about what the anatomy looks like. We're not terribly interested in water diffusion. We're interested in using water diffusion to figure out what the tissue architecture is. So in the DTI experiment, what we'll do is we'll probe diffusion in a minimum of 6 non-collinear directions. So that's so the diffusion signal is represented by this dotted line. We're measuring the diffusion-weighted images in a minimum of 6 directions, and you can see that when we're probing diffusion parallel to the axons, the signal is low. When we're probing diffusion perpendicular to the axons, the signal is high. Then we take this information and we construct a model of the pattern of diffusion in this voxel. And for the diffusion tensor imaging, this model is a 3D ellipsoid. An ellipsoid is an ellipse that's rotated on one axis. And this ellipsoid can be described by 3 principal axes, which are termed the eigenvalues. The orientation of these axes are termed the eigenvectors. The primary eigenvector, or sometimes referred to as the axial eigenvalue, refers to the orientation and magnitude of diffusion parallel to the axons. The second, and not shown on this slide because it's in 2D, the second and third eigenvalue and vectors refer to diffusivity perpendicular or orthogonal to your axons and is sensitive to diffusivity in the most restricted orientations. So for example, your second and third eigenvalues are often termed radial or transverse diffusivity and are sensitive to the degree of myelination. So bringing together all the elements of modes of diffusion and the diffusion tensor, we once again have our three modes of diffusion: isotropic, isotropic restricted, anisotropic. The DTI model, the diffusion ellipsoid for the isotropic unrestricted diffusion, and you can think of this ellipsoid surface as being as representing the mean distance traversed by water molecules, and it's a sphere for the free water unrestricted isotropic case because the mean distance in every direction is equal. For the isotropic restricted case, it's also a sphere because the mean free path in every direction is still equal, but it's of lower magnitude, so it's a smaller sphere. In the anisotropic case, this situation is modeled by an elongated ellipsoid where the longest axis of the ellipsoid is parallel to the axons, and the magnitude or the length of this axis along the longest dimension is related to the diffusivity parallel to the axons. And these diffusion ellipsoids are mathematically represented by the diffusion tensor, which is a 3x3 matrix which describes the 3D pattern of diffusivity. It's a symmetric matrix, so there's 6 unique elements, thus the minimum requirement that diffusion be probed in 6 directions in order to solve for the 6 unique elements of the diffusion tensor. So these are the familiar DTI maps that are created by this model. On the top row, I have the 3 eigenvalues. This is the axial diffusivity, and these two are the second and third eigenvalues representing diffusion transverse or perpendicular to the axons. If you take the mean of the 3 eigenvalues, you get the familiar directionally average diffusivity, sometimes termed the ADC. The fractional anisotropy measures the degree of anisotropy, that is the divergence from the isotropic case. So you see in the corpus callosum and the internal capsule, fractional anisotropy is high. And here is the color-coded fractional anisotropy where we assign a color to different directions, and you can start appreciating the orientation and positioning of different white matter tracks. So one thing I want to point out is that in these color FA maps, direction is not uniquely specified by color. So if you look in the corpus callosum, in the center it's red, indicating tracks are going left-right, but lateral to the midline are these 2 yellow regions, and they're both yellow on the color FA map, but if you look at a vector plot of the primary eigenvector, you see that the eigenvectors over here are oriented in this orientation, and on this side of the brain, they're oriented equal and opposite. It's a reflection. So that's something to remember when looking at a color FA map, is that it's not a complete representation of the axon orientation. And this image of a vector plot brings us to our next topic, which is fiber tracking, which is something we naturally do with our eyes when we look at a vector plot like this. When we look at this corpus callosum, we're not thinking about individual voxels. We are seeing it as a coherent tract because these voxels are all logically connected together. So So that's our next topic, whole brain tractography. This is a pretty image. I want to start by defining two terms that are often thrown around when people are discussing fiber tracking. Fiber tracking strategies, whether it's DTI or more advanced Hardy fiber tracking methods or diffusion spectrum imaging fiber tracking methods, can be divided into deterministic and probabilistic algorithms. Deterministic methods take the best estimate of fiber direction and run with it. So if we have 3 diffusion ellipsoids in a row, and they're all indicating that the direction of least restricted diffusion is left-right, the fiber tracking algorithm will connect them left-right without any deviation. Probabilistic fiber tracking algorithms incorporate an estimate of the uncertainty in the orientation of the primary eigenvector. So we're highly confident that there's an axonal bundle running left-right in these 2 voxels, but when we hit this voxel, the ellipsoid is suddenly bigger. And that indicates that we're probably a bit less certain that the axonal bundle is really running in this direction. It could be because the track is splaying. It could be that there's crossing fibers. There's something going on here that makes us less certain about the orientation of the axons. So what a probabilistic algorithm will do is diverge the tracks and incorporate that into the fiber tracking algorithm and explore multiple possible axonal bundles. Briefly, the overall strategy of fiber tracking is to first define a starting region, seed the starting region with starting points, follow the primary eigenvector. This is a deterministic algorithm I have illustrated on this slide, and we can follow it in the other direction. By far, deterministic algorithms are the most popular. They're the ones you're going to see on your vendor devices, on your MR console or offline. Things that are provided by companies and sold to you are mainly going to be deterministic fiber tracking algorithms. This is another example of using multiple regions of interest to define the motor pathway with DTI fiber tracking. The first step is to define a region of interest in the cerebral peduncle. I don't know if you can see the yellow region of interest drawn down here. And then we get fiber tracks going all over the place. We can further restrict it to the motor pathway by drawing a second region of interest in the posterior limb of the internal capsule. And we can further restrict it to the motor pathway by defining a region of interest in the precentral gyrus. And I'll come back to later why fiber tracking only, DTI fiber tracking only shows a small portion of the motor pathway. Just as a reminder, diffusion MR fiber tracking provides structural information. There's no functional information inherent in DTI or any diffusion MR fiber tracking information. You need to add functional information, and that can be in the form of historic functional information from your anatomical knowledge of the location of specific tracks or an MRI atlas, or it could be subject-specific functional information from fMRI, MEG, cortical stimulation. The better your source of functional information, the better your fiber tracking will be. So if you have subject-specific information, that's a lot better than making assumptions about the anatomy of a particular patient. Here's an example from Greg Verona of agenesis of the corpus callosum. This is, you see a nice example of fiber of the Probst bundles coursing anterior, posterior. Lissencephaly, you see a concentration of fiber tracks when tracking up the internal capsule. They look like individual brushes, and you don't see the defined structure going out to multiple gyri and cortices as you do in the normal brain. And the next few slides, I'm going to bring you through some examples of using DTI to characterize development. And as we go through these slides, the techniques that we're using for measuring the brain become more and more advanced, and it becomes and the information becomes richer and more interesting and leads to further questions that can be addressed with advanced diffusion MR. So this is a plot of mean diffusivity and anisotropy as a function of age from during the first decade of life, and mean diffusivity rapidly decreases and continues decreasing. Anisotropy increases and continues to increase, and this is because of changes in water content, premyelination, myelination, axonal density, axon diameter. All these processes are occurring during development and affect the microstructure of the white matter. If we take a closer look at fractional anisotropy and mean diffusivity in different regions of interest, these are in premature newborns. In the anterior internal capsule, the posterior limb of the internal capsule, the centrum semiovale, the external capsule, and the splenium, we see a similar relationship in tracts that are largely unmyelinated. Fractional anisotropy goes up between 30 and 45 weeks gestational age. Mean diffusivity goes down. So diffusion changes can occur from some of the other factors that are driving diffusivity other than myelin, including axonal density, axonal diameter, and possibly the beginning emergence of myelin during this time span. We can also use DTI fiber tracking to, in this preterm cohort, perform track-specific measures. So here I have a plot of fractional anisotropy versus age between 30 and 45 weeks gestational age in the motor pathway and sensory pathway. So these are measurements that are taken from a 3D region of interest defined by motor and sensory fiber tracks from the internal capsule up to the centrum semiovale. And as expected, fractional anisotropy increases and in both tracks. What we can also do with fiber tracking is take a closer look at fractional anisotropy along the tract. And a tract is not a homogeneous structure. There's in the internal capsule, fractional anisotropy is higher than closer to the cortex. And here I have plotted the motor and sensory fractional anisotropy in a 29-week gestational age premature newborn. And here is a 42-week gestational age newborn. And as expected, fractional anisotropy increases. The overall arrangement where the internal capsule has higher fractional anisotropy than the cortex remains. But we see the emergence of this dip in fractional anisotropy. And the question is, why do we see a dip in fractional anisotropy in the centrum semiovale? And the answer is that there's a problem with the diffusion tensor model. DTI is a single fiber model, and in the centrum semiovale, you have the intersection of motor, callosal, and association pathways, and these other pathways besides the motor pathway start emerging during development and cause the diffusion tensor model to fail. You can see in this picture these black spots where fractional anisotropy is abnormally low. This isn't because there's an absence of white matter here, it's because it's at the intersection of multiple crossing fibers, and the diffusion tensor model fails. So what do we do about this? We use high angular resolution diffusion imaging, which is one step beyond the diffusion tensor imaging model. And in a nutshell, high angular resolution diffusion imaging is very similar to DTI, except we probe diffusion in many, many more directions. Dozens, usually more than 50 directions. And from that, we can infer a more complex pattern of architecture. We can infer multiple crossing fibers. If the pattern of diffusion looks like this, we can infer that architecture. And in summary, DTI has a minimum of 6 gradient directions. HARDI, high angular resolution diffusion imaging, requires over 50 gradient directions with usually higher B values. So this is a return to the centrum semioval, where we have HARDI reconstructions of this spot with abnormally low fractional anisotropy, and we see where there's low fractional anisotropy, this is occurring not because there's an absence of white matter, but because the white matter is complex and there's crossing fibers. We can see motor, probably the superior longitudinal fasciculus and callosal fibers all intersecting in this one voxel here, causing fractional anisotropy to drop out. And I'll leave you with one more example of what HARDI enables us to do. We've discussed a lot, and the literature is full of studies looking at the motor and sensory and visual tracks, because these are important sensory and functional pathways that are important for development and life in children. But there aren't a lot of studies with diffusion imaging on the auditory radiation, and this is also a very important sensory pathway. The reason there aren't many studies on the auditory radiation is because it's a small tract that intersects a larger white matter structure. Specifically, this is the auditory radiation going from the auditory cortex, Heschel's gyrus, to the thalamus, and it's described in this slide by HARDI tractography, and you can see that it intersects the inferior longitudinal fasciculus, and diffusion tensor imaging at this intersection will completely fail and not enable you to delineate with fiber tracking through it. And this application of HARDI fiber tracking opens up an avenue of research into a sensory pathway that's previously unattainable with traditional diffusion tensor imaging. So look for HARDI and other advanced diffusion MR techniques to increasingly be more push button and available on your scanners, and I'm sure the post-processing techniques will follow in the near future. So in summary, what is diffusion? Random motion of water molecules. Why do we care about diffusion? Because we use it to probe for tissue microstructure and architecture. How do we make a diffusion-weighted image? We alter a spin echo sequence with 2 pulse gradients at 2 time points to observe the movement of water between the 2. What is anisotropy? It's a directional preference of diffusion, and it allows fiber tracking. What is the diffusion tensor? It's a 3x3 matrix which describes the 3D pattern of diffusion. Why does the diffusion tensor model always work? No, it fails to accurately depict crossing fibers because it's inherently a single fiber technique.